Boom, and we are live. At least I think we're live. Anyway, if someone in the chat can let me know if we're live, otherwise I'm just sitting there prattling to myself in my room again, as per usual. So are we live? I think we probably might be. So welcome to the first ever live stream on either Conspiracy Cats or Baldy Cats. But this isn't my show. It might be my channel tonight, but it's not my show. Tonight I am joined by somebody, if you don't know them, you really need to get to know this guy. He is one of my favorite creators and undoubtedly, in my mind, the smartest creator that there is out on YouTube. His name is AB Science. He's smiling away next to me, to my left or right, depending which way you hold your phone around. I'm going to introduce him. And AB, I'm sure almost all my subscribers know who you are because you are, pretty prominent on the scene at the minute. But for those who don't, just give everyone a bit of a background to yourself.
Yeah, sorry, I'm kind of looking over to my left a bit because that's where the kind of live stuff is going on. I hope that everyone can hear us. Yeah, hopefully. Yeah, right, cool. Yes, I'm AB Science. I have this little YouTube channel and I'm a physicist. I do things and I talk about flat Earth and all that malarkey, as you would expect, me being on Conspiracy Cats or Baldy Cats channel. But I kind of do just little educational things or little thought experiments to kind of see what interesting thing we can get out of flat Earth, really. So that's me in a nutshell.
And I think the idea for this show come together because me and AB Science are both heavily involved in education, but very much on different sides of the fence. I've been a teacher for not far off 20 years now, teaching people up to the age of 18 years old. AB Science is on the other side of that fence, teaching postgraduates. And in some of the conversations we've had, it's kind of become clear that a lot of flat earthers, a lot of the questions they ask, a lot of the misconceptions that they have arise because of the way they're taught at school, because of the way science tends to get watered down at school, because it has to be, because it is complicated. That when they have nothing more than that watered down version of science and they get a little bit, they want to get a little bit further advanced, they start to draw some bizarre conclusions, like, for example, the Earth being flat. So this is a new show where we're going to take those misconceptions and just deal with them one at a time. It's not going to be a long stream. We're not going to be on here for hours and hours. You know, I mean, we were talking before. We think it will probably be about 40 minutes, 45 minutes. And tonight, well, what's the subject we're talking about tonight? What's the topic of misconception tonight, AB? You tell everybody.
Well, so tonight we're going to start off by just having a look at kinetic energy. And this comes from some misconceptions, you know, the kind of thing around the Earth rotating, and if you go in one direction or in the other direction, then the difference in kinetic energy would change, and weird things like that would happen. So if you're accelerating with a fixed amount of work in the same direction as the rotation of the Earth, then you would expect a different result than going in the opposite direction. And there's the obvious misunderstanding of reference frames and things, but we're going to look into kind of a few different problems, and we're going to explain what is going on. Precise, yeah.
Okay, so I think what we said first, we were just going to say hello to one or two people in the chat, see what's going on, and then we're going to bring up the comments that kind of sparked this from a flat earth called Ryan Q. Vincent, who's been on both our channels, isn't he, with similar questions, and it's his comment we're going to sort of address. But let's just say hello to everybody. And while we're doing this, you know, sometimes I'll be talking more than AB Science, sometimes he'll be talking more than me, but the other one is always looking out in the chat for interesting questions. So if you've got some questions you want to ask, then fire them our way. But who have we got in there? Let's have a look at all of them. Gary Lowe. Oh, Gary Lowe says, could we please turn your audio up a bit?
I am working on that, and I was just fiddling with that, but accidentally turned your audio up.
Oh, you made me louder. Excellent.
Yeah. Right. There. Oh, crap. That's the wrong one. I thought we were going to do so well with the technicality of things, but no.
I think you've done a great job. You've done a great job. Oh, we've got Brainy Beaver in, Arctic Haze as well. Oh, and Bill Ashby. There's a lot of people here I thought had spanners that aren't coming up having spanners. I thought Bill had one, and and Brainy also. But if you do have a wrench, and anybody comes in, obviously I trust the people on my channel to use those, you know, correctly. And if you feel somebody deserves it, you know, don't feel shy. Obviously, if someone's coming in and discussing but just disagreeing, fine. But any sort of nastiness we want to keep out of the chat, I think. So if you've got a wrench, feel free just to use it. I trust you implicitly. Anyway, so
I'm just going to check my audio and make sure it's all right. I'm kind of mixing by eye here, and any kind of audio professional will know that is not on, but I have no other choice when I'm doing that live. So I just want to do a shout out, see if everything and the audio levels are all right. Give me some feedback. But in the meantime, Caps, go ahead, and shall we get to that question?
Yeah, let's get to this. So this is a comment that started it off. So Ryan Q. Vincent talking about kinetic energy, and what I like about Ryan Q. Vincent as a flat earther is that he's trying to think using physics. He might be getting it wrong, but he is trying to think. So I'm going to read out his comment. Here we go. I want to get your attention about your misunderstanding of reference frames when applied to the real world of moving objects. You are aware that reference frames are purely imaginary and you cannot change any values in them as they have no real world effect. To just make it clear, have you ever seen any scientific science evidence comparing showing?
Yeah.
Comparing showing that the acceleration of an object with a fixed amount of work that gives the same relative speed result forwards and backwards. This is a long comment. This is a very long comment. I'm going to cut to the chase with this. And I'm going to start here, which says the issue. All right, so we can get that one on, AB, the next slide. Which says the issue is the kinetic energy of moving bodies, right? It's not linear. What he's basically saying is, in a nutshell, if you try and measure the kinetic energy of a car that's driving on the Earth, if the Earth is spinning, the kinetic energy he thinks he calculates doesn't go with what we observe, doesn't go with what we see. He thinks there's a problem with kinetic energy on a spinning ball. So what we're going to do is we're going to look at why he has that problem, and it's down to the likes of me. It's down to the likes of the teachers at school. We're going to show you how we teach kinetic energy at school, and I'm going to set you a problem now. I'm going to see how quick you are in the chat to be able to get the right answer to this question. And then using that, we'll see what the misconception is that he's got. And then I've got to pass it on to the brains of the operation, who's sat just next to me there, who will be able to explain this away at a higher level. So here is for everybody in the chat. This is how we do kinetic energy when we teach it at school. Have we got the first slide up there, Mr. AB Science?
First slide is up.
Right. So I'm going to explain the question to everybody. I'm going to give it, while we go back to the chat to answer some questions, I'm going to give you maybe 2 minutes, 3 minutes to come up with the answer to this question. So a typical higher tier GCSE physics question would be something like this. We have a ball on a ramp, and we want to know how fast that ball is going to be rolling when it rolls to the bottom of the ramp, when it's got to the bottom of the ramp. Can we have the next slide on, please?
Yep.
And all we are given is this information here. We're given the mass of the ball, we're given the angle and the length of the bottom of that ramp. And we have to figure out, remember, the speed that ball will be traveling when it hits the bottom. Now, if anyone is studying GCSE and you're watching this and you think, oh, that looks a bit tricky, this would be sort of your grade 9 triple physics question, but it is something that is solved purely using the skills that you pick up at school. A combination of skills, but purely using the skills that you pick up at school. So how long should we give them, AB, to answer that?
Well, I'm kind of looking over the screen where actually everything is on. We've got quite a big delay between what we see and what they see. So thinking by the time it caught up to the screen we're on right now, yeah, I'd say then from that point, I'll say 2 minutes.
Should we quantify? Should we take 2 questions from the chat each, and that will give people in the chat enough time to come up with an answer, and then we'll go through how it's solved. What do you think?
Yes, I did notice in the chat. Asked the question is frictionless. Yes, it is frictionless. Okay, we're taking your typical kind of GCSE. For the international viewer, this is what the exams you would take at the age of 16. So yeah, we're taking a very basic situation.
Stephen Rose asked as well, assuming the normal value of G. Yeah, we on an exam paper you'd be given 9.81, but if you're not, there's nothing wrong with just assuming 10, even at that level, at GCSE level, there's nothing wrong with using 10. So we'll get 2 questions. I tell you what, if you can tag AB Science or myself into a question, and we'll take 2 each, and then I'll go through how that problem is solved, and how that leads to the misconception that Mr. Ryan Q. Vincent has got. Now, are the questions coming in? There's a bit of delay. I might see if I can make some funny noises with my hands while we're waiting. Well, while we're waiting, AB, what have you got on the horizon at the minute? What's your next video?
Right, so I've just recorded and cut a video that I've just released for my patrons, and it will be out on the main channel soon. And this is, and actually this is kind of an example for those who are not familiar with my channel. And what I do is where we just take a bit of flat earth rhetoric, and I try to find what we can learn from it. And in this case, I'm taking the infamous black swan image, and I'll be using that to actually talk about the basics of refraction, and derive simple things like Snell's law, and do that empirically. And then we have a look at what the impact has as you increase the kind of as you increase the number of interfaces, and what happens when you have this gradient in the refractive index. And to kind of then show qualitatively for now how it is that we can see a horizon behind those oil rigs rather than in front of those oil rigs. There's also just a little kind of approach on the modus tollens thing, which they haven't really understood. But that will be coming out soon, and that's, I think, going to kick off a kind of longer treatment of optics. And I'm currently in the early stages of just doing the basic, writing a script for the basic things around how lenses work. But I wanted to establish Snell's law first, and then go into lenses, and then, yeah, I have to see where it goes, really. Diffraction limit is obviously going to be one if we're talking flat Earth, and Rayleigh criterion and all of those things. So, yeah, that will be it. And then I've also naturally still got a few videos on, if you're not familiar with him, a guy called Theory at Apophysis, who talks a lot of nonsense about magnetism. I've still got about 4 of those videos in the pipeline, but I'm giving them a bit of a break because they're very dense, and yeah, they make you want to hurt yourself a little bit.
But I mean, everything you do, I'll stress to everything you do is very like the science is so spot on, isn't it? Everything you do.
Well, it's I make my mistakes. Don't worry. But most of them is kind of like I kind of use oversimplifications, or it's where I just ad lib things and kind of like, oh shit, not quite supposed to say that. But yeah, I try my best to make it all nice and accessible as well.
I'm just thinking what we perhaps should have done. Is there any way we could, while we're talking, we can get the question back on the screen, just so people can have one final crack of answering it before I go through it? Because I think some people are asking what the mass of the bore was, etc.
Okay, yeah, we'll bring that back up.
Turquoise Laura, always a massive help, who's in the chat there, and you are amazing. You've come up with a really good point. Can I turn off the slow mode? The answer is no. It's not because I don't want to. It's because I don't know how. It's my first live stream, and I genuinely don't know how to turn it off. So I'm going to have to learn that for next time, so I apologise. Right, we're going to go to the answer, how that's solved, in about a minute's time while you're working away. Let's see what answers you've got in the chat. Oh, and I'm going to say thank you, Stephen Steen, as well. Thank you very, very much. I would say Conspiracy Cats is the worst channel, not Baldy Cats. But thank you very much for that. Dr. Kent Hovind, yeah, a few questions asking about Kent Hovind. He's refused to debate me again, so that's not going to be happening, unfortunately. I think he wanted to do a video exchange only. Any other questions? We've got Ross Hopkins says 5.32 meters per second. Let's have a look. not many other answers, but then maybe there's a little bit of lag. All right, should we go through how this is done then? Okay.
Yep. Okay. I actually can't remember what the answer is. So, next slide, I presume.
Okay. Well, yeah. 1 second. So the next slide. Yeah. For anyone watching the chat, what I'm telling you now is how it's taught at GCSE level. You know, there'll be lots of you wondering about the effects of friction and wondering about the effects of air resistance and all sorts of stuff. You know, this is GCSE level science, so it's making things as simple as it can for the kids. So what do we teach the kids? Can we go on to that next slide then? Have you got the, let's say, conservation of energy at the top? I'm looking at something different. All right. The whole issue, and you'll remember being taught this at school, the whole thing we drill into the kids over and over and over and over again is that energy can't be destroyed, it can't be made, it can only be conserved. And AB Science later on is going to talk about how this leads to a misconception. And it was AB Science that taught me this. That's the sort of level he's working at. He's very, very good. But we talk to the kids about conservation of energy, and we look at the fact that the ball at the top of that ramp has gravitational energy, and the ball at the bottom of the ramp will have kinetic energy. And because energy is conserved, the gravitational potential lost as it comes down the ramp is going to be converted into kinetic energy. Now, you can see under that there that we've got the two equations for each one. We have mass times gravity times height on the left for gravitational potential, and you can see the kinetic energy equation on the right. Nothing too complicated there at all. So what we need to do is figure out what the gravitational potential energy of the ball is, and then that will tell us what the kinetic energy of the ball is at the bottom, because they're going to have to be the same. So how do we do that? Next slide. Well, if we go on to the next slide, we're given the angle of the ramp and we're given the length of the ramp and a simple bit of trigonometry. We are looking to calculate the opposite, aren't we? We know the adjacent. So tan 30 times 21 is going to give us, I put the working out on the top, haven't I? It's going to give us 12.12 meters. So that's how high the ball is. So if we go into our next slide again, we can now put that into this equation here. Okay, we now can figure out the gravitational potential energy because we know the gravity is always 10. I'll put it in here as red as 9.81, but we could have used 10. So we know that the energy, gravitational potential energy, the ball's got at the top of the ramp is 237.8 joules. Now, if we remember what we said before, the thing that's going to become so important later on, all about conservation of energy, we now know that the kinetic energy at the bottom must be 237.8 joules. Next slide, please. And we know the equation for kinetic energy is a half mass. And there's a deliberate mistake in there because there's no gravity, and that's a deliberate mistake. I've copied and pasted it's a half mass times velocity squared. Scrub out that little g, that shouldn't be in there. It's a half mass times velocity squared. Anyway, I've done the rearrangement right. I've just left that in from that's poor form. That I'll blame conspiracy cats. But anyway, we can rearrange that equation to pull out velocity, which gives us 15.4 meters per second squared. 15.4 meters per second, not meters per second squared. So that's how we would do it at GCSE level. And they're the skills we need. And anybody that's worked or done a GCSE, worked on GCSE science, etc., they would leave only having this as their sort of understanding of energy and energy transfer. And they would realize that to answer this question, the fundamental idea is a conservation of energy, that the kinetic energy at the bottom has to equal the gravitational energy at the top. Energy can never be destroyed, made. It always has to be conserved. And as we get into AB Sciences bit in a minute, you'll see the problems that causes. So did anybody get that? I've not been looking at the chat, AB. Does anyone get 15.4?
I think a few people have stated, yeah, I got it. There's a nice one, which is I got it. Whoop, should have had more faith in myself. And actually, I think that really summarizes a lot of people's issues with maths. It looks really complicated a lot of the time, but sometimes if you just plug through it, it actually becomes, you'll be surprised on how easy it can be. Most of it, it's about a fear actually approaching those problems rather than actually doing it. It's, I think fine example. I had a student today who was really struggling with a particular problem that was set. It was not maths, it was programming. and yeah, he was really struggling with it and just completely panicking. And I just try doing it. And 10 minutes later, they had it all done.
Well, I think at your level, I mean, you know, things are incredibly complicated, but does it still hold true? Like the question we've just got there, Stephen Steen says got 32.6. Close, Stephen. The problem that we've just done, the GCSE one, is simply just a number of different steps utilizing basic skills. So, you know, step one, utilizing trigonometry. Step two, rearranging an equation. You know, at your level, obviously the equations are going to be more complicated, the rearrangements, but is it still the same thing? Is it just a series of steps using different skills?
Well, the thing is, and this is something that I have issues with at GCSE or stuff like that. It's you know, you get set a problem, you get given some values, and then you get asked to find the answer. But in physics, we don't really bother with that. And then there's a bit of a classic joke around, well, there's a key difference between the engineers and the physicists. Is the engineers are happy if you just give them a list of values, and you know, they'll figure out the answer for you, and that's great. But for physicists, we don't care about that, right? If we've got mgh is equal to half mv squared, that's it. That's where we leave it. We don't really care that much about actually figuring this stuff out. They're just numbers, and we care about the relationships. We care about, you know, the equations that change, and a number doesn't describe change very well. So that is a little bit different, but yeah, a lot of the kind of, if you're trying to figure stuff out, most of it, yeah, it's just about rearranging it and breaking down the system in such a way that it becomes solvable. You know, I work in nanomagnetism, and we deal with, you know, the central equation to our field is something called a nonlinear differential equation, and you cannot solve it on a piece of paper. You can't just plug in some numbers and expect a result, because it's not possible, because because the dependent variable is also one of the independent variables. So that completely falls apart. But you then have to go and start making some approximations and then use some really big, shiny, expensive computers to try and figure out the best approximation to a solution. But yeah.
You can't solve it by pouring water on a ball then?
No. Funnily enough, no.
Well, I just want to say, John Rapp, thank you very, very much. We are CGI, but thank you very, very much, mate. We appreciate that. Right, so we've got the idea of what Ryan Q. Vincent will have picked up at school, the type of skill set that he would possibly have if he's retained it, and that's about as high as we get at GCSE level. But that has led him. Can we look at his comment again, just to see?
Yeah, one moment. I just need to pull that up. Go right to the start. Okay, yeah. So you can see my screen now, can't you, Kat?
Yeah, there's a bit of a delay. Have you got the comment up?
Yeah, but you should. I think you should be able to see that now.
I've got it up in mind, so we can. Yeah. So essentially, and because I want to make sure that I'm explaining this, because it's quite a wordy one. I don't just want to read it out. You know, my understanding of his comment is that when we do these calculations for kinetic energy on a stationary globe or a stationary flat plane or whatever, then we get exactly what we see in the real world. But when we do the calculations to find the kinetic energy of something on a globe, when we are watching from space, we don't get this conservation of energy, and it all goes tits up. Am I right with that, or can you expand on that?
So, from my understanding, what the issue is here. So, for example, we've got point 2 that is there. Well, point 1 and 2. A fixed amount. So, just to make it clear, have you ever seen any science evidence showing that the acceleration of an object with a fixed amount of work that gives the same relative speed result forward and backward for a stationary reference frame. So yes, we can understand that he understands that, yeah, that is what happens, that in a stationary reference frame, you get the ball, it doesn't matter what direction, you get the same change in velocity. And why we use this ramp example is because it's a fixed height and therefore does a fixed amount of work. But then on 2, he talks about this moving reference frame. And if we were to perform that experiment where we have the ball accelerated towards the front, that's the fixed amount of work being done into it, you should get a different result as if you were to accelerate to the back of the train. And this is because of that v squared term. And we will kind of show that mathematically where his misunderstanding comes in shortly as well. But I hope everyone is on board with, but yeah.
I want to say thank you to Sergey in the chat. He just has a question. Should we not have used sine instead of tan in that example?
Yeah,
you need to know. Well, we could, couldn't we?
Huh?
But if we've got, so which example are we looking at? If for sine, you need to know the hypotenuse, don't you?
Oh yeah. It's because you use, yeah.
We had the adjacent and we were looking for the opposite. So we needed to use tan for that. Yeah, we didn't know the hypotenuse for sine. But I don't think I left the question on the board long enough for...
yeah, I've just pulled it up again. Yeah. All good.
Yes. But thank you anyway, Sergey.
I didn't even check the work, so... right, okay, so... let's put that back onto the main screen so I can safely switch windows.
Just looking at the diagram there, the length at the bottom, where it says length, you could interpret that as being the length of the hypotenuse, couldn't you?
Yeah.
That's the length across the ground. That's what that was representing. So that's my poor PowerPoint skills, I think, more than anything else. So note to next time, get my PowerPoints a bit better. Right. So there we are. So you're going to talk us through how Ryan Q. Now we know what his misunderstanding is, or what his problem is. You're going to talk through how people at a higher level, understand that it's not an issue, and then hopefully he might listen this time, because you've explained this to him before in a response video, I know, but off you go, mate.
All right. So I think I was going to start with a proof of why kinetic energy is actually 1/2 mv squared, but I think I'm going to skip that. Mainly because there's one small step in there which requires calculus, and let's just not do. However, I will just say that if we solve this problem without actually plugging in values, I think that's a good starting point. So have I got the right thing? Yeah. Okay, so everyone can just ignore this. So we have the expression if we take the expression we previously had, so we have mgh, which is the mass of the object, g 9.81 magic acceleration downwards, and then is equal to 1/2 mv squared. So here it's just that simple rearrangement, but it's just I wanted to really highlight just that key result. So if we want to figure out the change in velocity from a change in height, so we start off with just getting rid of this half, sticking that on the left hand side, and we cancel out these m's, and then just move that there, because this is a result we're going to refer to later on. So we take the square root of all of this, right, and we get that. So that is our expression for that change in velocity. But we want to talk about the slight misunderstanding that Mr. Vincent has, but this is a key result that we will be referring to. So now we have the same problem. Okay, I haven't got a shiny ball or anything, but we have a ball on top of a ramp which has some height h, and it is going to roll down, and we want to figure out what the energy is when it hits the bottom. But the whole frame, the whole experiment, is being performed on a train which is traveling at some speed u. So we start off with our expression where we can no longer have the simple mgh is equal to 1/2 mv squared, because we have an initial velocity as well. So at the start of the situation, it is traveling at some velocity u. So we need to introduce that term into all of this. That's 1/2 mu squared. Okay. So
that gives the total energy. So I just want to make sure that I'm keeping up with this also.
Yeah.
So what you've got on the left, you've got the gravitational plus the kinetic.
Yeah.
And you're talking about the kinetic there provided by the moving.
Yeah. So this is the energy at the start, right?
Yeah.
And then this is the energy at the end. So we have this velocity, which is provided by the fact that the train is moving. Now, what I'm about to do, for people in the chat who are going to know the answer, this is going to go wrong. Okay, from a presentation perspective, I would prefer to not say that from the start, but I know people will start shouting at me if I just go ahead. So I am fully aware that what I'm about to do is wrong. So if we do that same cancellation, we get rid of these m's, right, because they're on both sides. And then we multiply the whole thing by 2. So we get rid of these and then get 2. Okay. Now, v is that final velocity. And what v represents, it actually is the initial velocity, which is u, plus the change in u. Okay, so on the right-hand side, we can actually say that v squared is equal to this squared. And when we plug that in, move that there, and when we expand that out, we get that u squared plus 2 delta u plus squared. Okay, so this becomes this when we expand those brackets out. So we now get rid of that and move that in there. Now we can see straight away that these u's cancel out on both sides. But we are still left with lots of weird terms. So if we rearrange this, what we can see, well, if we have a look at this, we have a term here, which is delta u squared. We have this term here, which is delta u, and there's this term where there's nothing. So this actually reminds us of a quadratic equation, where we would normally have ax squared plus bx plus c is equal to 0 or something else. Okay, so that's actually what we have. So we move this across there. I'm just going to say minus 2gh 0 on the start there. Okay, so this has two solutions because we have the square term. So we actually find that for this to hold, that delta v must be equal to v squared plus 2gh and minus v. Or the other solution that exists is equal to now, do not be afraid if you don't fully understand what's happened here, but this is just from a standard solution you can find using the quadratic equations. But this is a problem, because this shows us that actually this is the ball accelerated forward, and this is if it were to go backward down the train. But this shows us that that change in velocity is actually dependent on that initial velocity. I think I did a whoopsie there with some stuff. Yeah, I accidentally switched from U to V somewhere midway through. And we get the same here. Now, what the result of that is that if the initial velocity is 0, then we find that in... Why am I writing format? I'm an idiot. When the initial velocity is 0, we get the same change in velocity regardless of direction. But in this way, we get different velocities depending on the direction and depending on the initial velocity. And this is a problem because this is not what we observe. Because this is essentially saying... So this basically says that... We're back on the main screen, by the way, Kat.
I'll stop picking my nose.
Yeah, stop picking your nose. So what this is saying is that if you have this ramp and you're sitting on a train, if you have this ramp, direct this ramp towards the front of the train and you let the ball slide down, then you get a certain result. And you get that, say, the ball accelerates, or the change in velocity for the ball increases by, say, 10 meters per second going forward. And if you were to reverse the situation, you sitting on the train, you measure the same thing as it going back if you roll it back. But an observer on the platform would not observe this. They would see that the change in velocity as you accelerate to the front of the train is different than it is if you were to send it to the back of the train. Now, this is problematic because across reference frame transformations, a change in velocity has to be conserved. So there appears to be something completely wrong. Now, Ryan Q. Vincent's approach is, well, we do not observe this. We observe the same change in velocity in all directions. Therefore, we are not moving. And you'll see that this example is completely incorrect. And we will actually go to the correct shortly.
So just to sum up from from my point of view that I'm following, essentially the maths is showing that if he's correct, if you're on a train and you roll the ball forward with a certain pace, a certain power, certain pace, it will set off at a different speed than if you turn around and roll the ball backwards on the train.
Yes,
according to him. Yeah,
which
obviously, and obviously though, and I'm just going to address this out. There's a few people in the chat before you go on to solve the problem, who that are quite rightly pointing out some things that we were talking about before. So, for example, we were talking about, or certainly you mentioned it when you saw the problem, that it's a really bad idea to be using a ball that's rolling because you've got the translational and rotational velocities as well. I think we mentioned the lack of friction, didn't we? Air resistance. And I think that the whole point of my bit at the beginning was to show that when you leave school, that is the kind of understanding, unless you go on to do A-level science, that is the kind of understanding you leave with. You don't go any deeper than that. You look at questions that are ideal, that don't have any friction, where you can ignore, balls rolling, etc. So that was a very, very typical, in fact, all the problems that were with it, that was a very typical sort of GCSE grade 9 question. And like the point of this, if you've come in a little bit late, is to show that when you learn stuff like that at school, you carry forward with you misconceptions that then can lead you to draw the wrong conclusion. So absolutely, the question was flawed in a million different ways, which is why people like Ryan Q. Vincent make these errors, if you like, and you need the kind of intelligence of somebody like the guy sat next to me to properly explain that away. So yeah, you're right. Everyone criticizing the question, That's exactly the point of this. So well done. Anyway, sorry.
And it is something that I was supposed to. It is something that I was supposed to mention. But yeah,
You're rolling, yeah.
Yeah, I forgot. Yeah. Right. So how are we on? Yeah, how are we on kind of questions from the chat? Do we have anything exciting coming?
Yeah. So should we give? Because we were never going to make this a long. Have you done with everything you wanted to do with the debunking of that question?
Well, no, there's one more. I will be showing the correct way of doing it.
Yeah, I thought we could have finished a bit earlier then. But should we say then, while AB Science is going through the correct way that this should be done, because these aren't going to be long streams. If this program, this show, whatever we're doing, we're looking to keep it less than an hour, aren't we? Around about 45, 50 minutes, something like that. So if you want to whack any questions in the chat now, and I'll make sure I'm busy writing them down, and then when AB Science is done, we'll just address any sort of questions that you've got. So I'll hand it back to you, my friend.
All right. Cool. So I am going to switch back to iPad. That's the wrong one. There we go. Okay, so you'll notice here that I've drawn the situation a bit differently. Now, I've got this expression here, and we have to remember that we said it was on a train. And if we're standing on the platform and we're trying to solve this problem, we have to remember that the train is a part of the system. So this is what the observer from the platform would notice. So we have our conservation of energy here again. So here we have the that is the potential energy of the ball on the object on the ramp. Now I've taken the kinetic energy of the train here. Now you'll notice that there's a capital M, and that is to indicate the mass of the train, and I used U and then U to indicate the velocity of the train, and then the subscript I to show that it's the initial, and then I use F to show the final. And then I've got the lowercase m for the mass of the ball or the object. I don't want to call it a ball because it doesn't roll. And then v as its velocity. And now we have a slightly different starting point. So the first thing we want to do is we want to write this in terms of the final velocity of the ball. So we just change that as 1 over 2 mv final squared is equal to mgh plus 1 over 2 capital mu initial. No, let's not do that. mv final, so plus 1 over 2 mv initial squared. There's a reason for it, because it's a bit tidier, and plus 1 over 2 capital M, so the mass of the train, and then I'll stick in brackets the initial velocity of the train minus the final velocity of the train. So this is how we set that problem up. Now first we just want to get rid of those 2's, those 1 over 2 even. Multiply that by 2. And we want to get the left hand side, we just want to get the final velocity. We just want to get the final velocity, so we kind of get rid of all of these m's there. Divide that there. Now, what we have to recognize again is that the final velocity is equal to the initial velocity plus the change in velocity. And that goes for the object, and the same goes for the train. Equal to initial plus change in u. And this also allows us to conveniently just get rid of these subscripts because they're just a pain in the ass. So we perform those substitutions in there, but we also recognize that the initial velocity of the train, and consider that at the start of the problem, the ball is at rest with respect to the train. So u is equal to v. So we perform these substitutions. So first we start with vf squared is equal to that squared. Stick that there. And then uf squared, move that across. Uf squared is equal to that squared. So you can see how we can make those substitutions. That's going to go wrong because I didn't leave enough space. That should be okay now. Okay. Now, what are the simple things that we can do to simplify this problem? Well, let's expand that out. Get rid of that because we got subscripts, didn't we? And that. Did I do a whoopsie? Oh yeah, I was supposed to change these to V's, wasn't I? That's what we said. Right, so we have inside the brackets, that becomes V squared plus 2V delta U plus delta U squared. And we have this minus sign here. So we change all that. And then we stick this into the equation. Now, first we see straight away that, oh shit, I just did something bad, that these cancel out. And that makes it a little bit tidier. Next, what we have to consider is that, well, we actually have to invoke another conservation law, and this is the conservation of momentum. So if we take that initial velocity, the object, plus the initial momentum of the object, sorry, and the initial momentum of the train, that has to be equal to the final velocity of the object plus the final momentum of the train. Sorry, I'm kind of mixing them up. And we rearrange this. So we have m ui minus uf on the left-hand side. So this is the negative of the change in, well, momentum. Well, no, not quite. So we have this, what's in here, sorry, that's the negative of the change in velocity, okay? And then when we move on the right-hand side, we've got the change in velocity of the object. So we notify that by dv. And we can rearrange that so we can get just du. So we divide this by capital M, stick a minus sign there. And that gives us an expression for du. And we can substitute that into the equation, which is up here. So we have our du there, so we replace that m over capital M v, and place, oh, that was a good cut, that with m over m, that's squared. So we end up with this squared, so that works out. And then we can start cancelling out, but first I just want to tidy up the bottom here. Ooh, my iPad is overheating a bit. Okay, so we can now perform some cancellations. So we see that this and this and this, that all cancels out. So we are left with getting rid of that. And we just get rid of these little 2's here. And then we can expand those brackets out. Let me just tidy up this equation a little bit. Right, so now we still have to do that little expansion on the left-hand side here. So we've already done this one several times, so we'll just say that's v squared plus 2v delta v and then plus delta v squared. Okay. Move that there. And we can see straight away that for some reason my tablet is struggling with rendering. This one and this one, they cancel out. And I'm dropped a minus sign here somewhere, sorry. And then this one and this one, they cancel out as well. So we are now making this scary looking equation a lot simpler. And as I kind of said earlier, sometimes it is just about doing the steps. Now we still have this term, because I said previously that I'm going to try and get rid of this dependence on the initial velocity. But we have to recognize here that m is the mass of the object and capital M is the mass of the train. The mass of the train is obviously way larger than the mass of the object. So m over m is actually really small. And because we're physicists, we can just say that's equal to 0. Because, well, it's too small to really count. And that allows us to finally get rid of that bit. And if you look now, if we take the square root of this, we are left with that same result as we had at the start.
Which is pretty impressive, mate.
Now, this is the kind of thing you would learn at A level, and you would learn again within your first couple of weeks at university. If you haven't gone past, GCSE, then it might not come across that you have to consider this properly, and that is where fundamentally a lot of the problems come in kind of flat earth reasoning here. And that is not it's not necessarily that they've completely misunderstood it, although in many cases they've obviously do, but in this case they understood a little bit.
Yeah.
But what is not taught a lot of the time is the importance of setting up your problem, because you sit your GCSE exam and the problem is already set up, right? It is already correctly set up, and you just plug in the numbers into the right equations that you might have to rearrange, but you have to pick your reference frames. You have to consider all the objects in the system that are important, and sometimes there are things in your system which are not important, and sometimes there are things that don't look important become really important. And this is a big problem in how Ryan would have approached solving this problem, is that he takes the example of where the observer sits on the train, he performs the experiment, gets a particular result, and then from the platform kind of repeated it, but just set the initial velocity to something. And he failed to take into account the fact that there is an interaction with a big ass train that's on there and that's moving. So yeah, that worked.
Well, what you said before about GCSE and excuse me, and having the problem set out for you, you're absolutely bang on. The question that I set before, we wouldn't have had to work that out. No GCSE pupil would have to work that out from start to finish. You'd be asked to use trigonometry to work out the height of the ramp. You'd then be asked to, what your equations were. You'd then be shown how to asked to rearrange them, etc. And you're talking about the same thing, just on a much more complicated level. And like I say, whereas someone who's only done science up to GCSE level, they would, if all their experiences are having things laid out so easily for them, and they're not having to be resourceful and think for themselves, if they're not going to even see a possibility sometimes that they've gone wrong or they've missed something. And obviously what you've done there shows that it's not easy. And I think sometimes a lot of flat earthers get upset because we say, you just don't understand it. Well, some things you do have to understand to the level you understand it at. Until you've gone through that with me, and you went through that with me this afternoon as well, didn't you? That's something I wouldn't have been able to just think through myself at all. And there's been other things I've come to you for help on just this week, even. You know what I mean? And which is why I think you're so useful in this community as well, because you really do know your stuff. But yeah, I mean, I think the ultimate conclusion is that Ryan is wrong because of misconceptions that has been ingrained in him when he was at school.
Yeah.
And he now needs to realize that Dunning-Kruger, I think, is a real thing. You might be confident that you know a little bit of science or maths from school, and you might have done quite well in your GCSEs or whatever. But if you can't see just how much more there is in front of you to learn, I mean, what you did there was a world apart to the question I gave, which was great for me because mine was easy.
Well, but the thing is, it also kind of illustrates the earlier point of what I said. Everything I did there, it was really, really quite simple algebra. And it looks really complicated. But actually, as soon as you start hacking away at the problem, and okay, the thing you kind of need to know is like, oh yeah, I've got to invoke the conservation of momentum in here. And that, it's those little things you need to know. But actually, mathematically, everything I've done is really trivial. It is just rearranging things. It was just algebra. And in fact, at the start, I was going to start off with, something just kind of showing some certain proofs which involved calculus and all of that. And I decided against it. This is all stuff, the actual mathematical operations that I performed in here, you would have learned before you started your GCSEs. It is just about not being intimidated by the problem. That's very important. Don't get intimidated by the problem. Just try it, and yeah, it does work.
Well, I think you've proven that ultimately that Ryan is saying physics says that we should notice this difference with a car driving on a rotating globe. And hopefully if he's watched this, he now realizes that physics doesn't say that. And that kudos to him for trying, but actually physics doesn't say that. So it'll be interesting. I think, next time I see him in the chat, I might point him towards this and see what his take on it is. But I have picked up some interesting questions, some for you, actually.
Okay.
Now, the first one from, where was I writing them down?
Oh, old school. You were writing them down, were you?
I was writing them down. Yeah, look at that. In a red teacher's pen. It's from Tusk. Okay, are you ready?
Okay. Oh,
we have.
From Tusk,
I think I've got an answer to this, but not that I've calculated it. Tusk says if you have a 9mm bullet traveling, a 9mm bullet that weighs 135 grams, or what did I say wrong there? That has a mass of 135 grams. It's traveling at 1,500 feet per second, and it travels 500 feet. How much energy will it have by the time it reaches a target?
I wouldn't be able to. That's one of those nonlinear things because of drag.
Sorry, and he did, yeah, and he's obviously a clever guy because he said we shoot in a vacuum.
We shoot in a vacuum.
Now, if we shoot in a vacuum, would that not make the 9mm, the size of the bullet, kind of redundant?
I don't know ballistics.
See, from my level, and this is where the whole Dunning-Kruger might come in on my part, right? Because I would say, and I'm hoping that you could correct me or someone in the chat might expand it. I would say that ultimately, if you knew how high the bullet was off the ground, then the total energy of the bullet is just going to be the combined potential gravitational energy and kinetic energy. And we've got everything we need there to calculate the kinetic energy, as long as we know how high it is off the. But obviously,
Yeah, but
it's
also
different, isn't it? But we can calculate that as well. The simple equation, we could calculate how long it would take to hit the target along the x-axis, and because we know the time it takes to hit that target, we know the speed and the distance. We could then calculate how much it's dropped because we know the time and we know the acceleration. So would it just be when it hits a target, the combination of kinetic and potential?
Well, yeah. If it's going to be a conserved, then yeah.
But what about on a globe? On a spinning globe, will it work?
But you've got a little bit. I suppose you've got a little bit of drop, and if you're just calculating the velocity, then you got to think about what component. But yeah, if we assume that the velocity doesn't change in that direction, and it's just a change in velocity in that direction, yeah, you would just have an increase in kinetic energy because of that small extra downward component that it gains.
Yeah.
Yeah, I don't know ballistics, but I presume that,
Good question.
yeah, it's a good question. But I presume, yeah, the same kind of principle apply, right?
So I've got some crack in there. Raven Looney says if we could stack a load of flat earthers on top of each other, which one would be the most dense?
Make a flat Earth density tower. Ooh. I don't know. I reckon. Oh god, that's too hard. Right, the hand will definitely be at the bottom.
It would be Anthony Riley, wouldn't it? No matter where.
Anthony Riley would be quite low down. I would imagine. Yeah.
Right, there's some names here. Oh dear me, I'm gonna get this. Is it? Channel deleted for this name. Craving Mordic says. He says, where do I plug the XLR? Now, given your name, I don't know like what XLR is that a microphone lead?
Sorry, what was the statement?
He wants to know where to plug the XLR.
Where to plug the XLR? Well, it is a microphone cable, but I'm not getting the reference of where it goes. Is it in reference to my my earlier screw ups on audio or something?
No, he just said where do we plug it? So I just assume it's a microphone lead. I think I don't know. It might be reference to
one end goes into your microphone or whatever outboard gear you've got, and the other end goes into your audio interface or your mixer.
Now, this next one, I really like this question. I really do, and it's from. If my handwriting wasn't so bad, I'd be able to tell you, but my handwriting is really bad. So if this is your question, can you let me know in the chat, because I wrote it down and my handwriting is so bad. I don't know what you think. I can't even read it. But he says, if you're traveling in a car at light speed and you turn the headlights on, right?
Mm-hmm.
What happens to the light in front of you?
It travels away from you at the speed of light.
It's amazing, isn't it?
Yeah.
It's absolute. Now, like, just because I assume we're talking about.
Oh, hold on. The car is traveling at light speed,
which we know will be impossible, and that would break the law of physics itself.
Yeah.
Because are we right that, just in simple terms, and because this is how I understand it, and I'm going to take advantage of you being here, that as you accelerate something towards the speed of light, because E equals mc squared, and as you're accelerating your kinetic energy, the E side of that gets bigger, but the speed of light is a constant, then you must gain mass. And therefore, as you gain mass, it takes more energy to accelerate you. So the rate at which you can accelerate slows down. So therefore, you can never reach the speed of light. Is that pretty much the explanation, or have I completely cut that up?
It's not quite right, but it is the correct conclusion.
Okay.
Yeah, so basically, because there's a few more terms, right? But basically, yeah, we have the we have a thing called the Lorentz transform, and yeah, this applies to mass as well. Well, yeah, it applies to the energy and therefore the mass. So yes, as you increase your speed, you do increase your mass. Yeah, so you got this really weird kind of thing going on because obviously you increase your energy, so you're more forced to move. Yeah. Basically, the reason is, yeah, if a massive particle were to travel at the speed of light, then its mass would become infinite, essentially.
So
and that's why it doesn't.
It's incredible that though, isn't it? And I've got a good question I want to ask, but I just on Earth, have we ever observed that? Have we ever observed, like when we're looking at particle accelerators or something like that, have we ever observed the mass increasing as we approach?
Yeah, absolutely. This is one of the big kind of evidence for it's very important in our body of evidence for special relativity.
Fantastic. Right, now another question for you. It's a good one. I must have the best names in the internet on my chat tonight, because
it's not. Quit asking me to.
Yeah, I'm gonna have to read this out. I'm sorry. I shouldn't be finding this so funny at this age. Yeah, quit asking me to sprinkle them titties.
Yeah, seriously. He comments on the shills quite a lot, and I'm pretty sure he's the reason why every fucking video gets demonetized.
Well, he's got a great question, and he says, similar question to the car one. If the plane is traveling at the speed. If the plane is traveling at the speed of light, which again we know is not possible, but a passenger then walks forward on the plane, so we're putting reference frames in here as well, I would imagine. What happens then?
Well, these are the problems when you're traveling at the speed of light. Also, the thing is, what happens at the speed of light is that length is infinitely contracted. So distance, kind of everything becomes infinitely small in a direction traveling.
Right. So there we go. So you can't travel, right? So
no,
the distance.
It just. I mean, it would be cool because if you could travel at the speed of light, then your distance is any distance you travel is 0, and it won't take you any time to get there, but from the observer's reference frame it would take you forever to get there. So yeah, weird things would happen at this if you were to actually travel at the speed of light.
Right. Well, we did say when we started this that these shows, if you like, we were trying to keep to about 45-50 minutes. We've been going over an hour today, but this, I mean, the plan is, isn't it, to make this a regular thing, but not always on my channel, sometimes on yours, sometimes we maybe on the shills, we'll bounce the show around.
Yeah.
But, you know, we'll always try a similar thing to address, if possible, you know, to address a misconception and then talk about how education at school can create that misconception, and then how clever people who are proper scientists like yourself can do that. So, and I just want to urge everyone, seeing as this is on my channel today, I have linked AB Science's channel in the description, and obviously by now, if you didn't know who he was before, you do now, and you'll know that he's well worth a sub for genuinely intelligent content. So please go and check him out. Have you got anything you want to say before we head off, buddy?
No, I think I'm good. I just want to highlight. Yeah, this is going to be a semi-regular thing, but we're not going to stick ourselves to a tight schedule. It's about, you know, subject matter has got to be everything. So we have a stream where we're just talking random crap, and we will be doing stuff when we think we really have something to bring to you. Okay, so we do have a few ideas for the next kind of a few broadcasts that will come out, and we will be discussing them. But yeah, there will be definitely more coming. Everyone that way inclined.
And I think so far, unless, I mean, we'll have a chat off air, and definitely if anyone wants to comment on the video to suggest changes to the format. At the minute, the format is obviously an introduction. We look at the problem, we look at how it's taught at school, we give you a problem, then, you know, to answer, and then AB takes over and does the explanation, and then we answer some questions. You know, that this is kind of the format we've figured out. But if you want to suggest changes to it, do that, please, because we'll be open to listen to it. But it's not going to be something where we just fire up and shoot the breeze for a couple of hours, because I just end up talking nonsense then, even more so than I have tonight. But AB Science, honestly, thank you for coming on and doing this with me. I've really, really appreciated it.
No, it's been fun.
Well, I have learned a lot, and I will sign off, and I will leave you to have the last word. And by the way, how do I stop stream? Oh, end stream there. Right. So when you give the go, I'll hit the end stream button.
Okay. Well, thank you all for coming, and hope you enjoy it. Hope you enjoyed this, and look forward to what you have to say. Thanks, and kill it.
Bye-bye.
See you later.
Oh, I haven't killed it. Are you sure? Okay, bye. No, that's not done it. Jesus.